Hi, my name is Ishita Raghuvanshi, and welcome to my physics public lecture review on Professor Zeb Rocklin's Science of Origami. So I took personal interest in this topic because origami is one of my hobbies and de-stressors, and I also noticed a lot of applications of origami in biomedical engineering, especially in the flat and deployed form, which is inspired by origami and is especially useful in product design, for instance, in heart stents and novel drug delivery methods. As an insight into Professor Zap Rocklin's research, his research focuses on the relationship between geometric structure and mechanical response. In this lecture, he covers the following topics. What are the properties that allow for the folding of complex figures? What are the applications of origami? The math of folding, i.e., crease patterns, mapping from paper to curvature, folding aesthetics, origami nature, and kurigami, which is cutting paper. The main idea of this entire lecture is how this cultural activity works and contributes to science and technology. So, going into the properties and applications of origami. For origami to occur, deformation must occur. That is, stretching and bending of the choice of material. Now, Hooke's law is essential to this. Hooke's law describes stretching, where it says that less material requires less force to stretch. Bending or folding says that a thinner material is easier to bend, i.e., a material that is 10 times thinner will be 1,000 times easier to bend. The material of choice, paper, is strong, flexible, thin, and creaseable, making it optimal. A fun fact is that the world record for the most number of times that paper has been folded is 12, which was achieved in 2002 with toilet paper. Some applications of origami are foldable solar panels installed on the International Space Station to minimize space, Kevlar bulletproof vests, heart stand that expands in surgery. Now, going into the math theorems and mapping that explain origami. So, when we get origami instructions, they're highly complex and have a lot of steps. However, they can be simplified into crease patterns to minimize these complicated steps, simply having mountain and valley folds that describe how a complex figure can be made. So, in this process, through mathematical analysis, which examines the vertices and the flat foldability, a very complex process can be simplified into just these shapes that represent the mountain and valley folds on a piece of paper. Now, four different theorems can explain the math behind origami. Makawa's theorem states that if a vertex is flat foldable, then the difference between the mountain and valley folds is only 2, as represented by the first figure. Kawasaki's theorem states that a vertex is flat foldable if and only if we can alternately add and subtract angles between the creases to get 0. In this case, adding up all the angles from A1 through A6 would give us a 0. The coloring problem is that no phases that share a crease can have the same color, i.e., no two phases that share a crease can be of the same color. In addition, there's also no self-intersection at an overlap. Now, these four principles define origami. Now, how can we take something as simple as one sheet of paper and make it into a complex 3D figure which has curved surfaces? For instance, a uh, 3D rabbit. Now, this is extremely difficult because of the Mercator's distortion. So, taking the globe, for instance, we can't take the globe and fully simplify it onto the map without having certain distortions. For example, um, Greenland being represented as bigger, if not the same size, as Africa, when in reality it's a lot smaller. So it's really difficult to take a curved surface and map it to a flat sheet, and shapes can be highly misrepresented. The Gaussian curvature can also be used to understand this mapping process. So if we look at the bottom figure, we can tell that a sphere has positive curvature, which means that it's really difficult to map from a sheet of paper to a curve. However, with origami, it's really easy to cheat this process and achieve the curves. For instance, take Tomohiro Tachi's process, who uses sophisticated computer generated crease patterns in order to tuck away paper and create a curved surface. Miura Ori also does a similar process where he uses repeating parallelogram folds in order to simulate the curves, tucking away paper, similar to Tomohiro's process. Now, this is very useful in a lot of different places. For instance, one application of Miura Ori's process is the Al Bahur towers, where the folding and unfolding of the panels, which have these parallelogram shapes, allows them to control heat reflections into the buildings. Now, some applications of origami in nature are in the folds of leaves and new petals, etc. Now, going on to about the further exploration of origami, we can look towards Robert Lang for this, who states that you can utilize packing circles for more complex shapes and fill in molecular crease patterns in order to create these large, complex figures. Origami has also enabled safer airbags. It has allowed for mirror folds in the James Webb Space Telescope in order to generate a lot larger, clearer image. For Tomohiro Tachi's research, he has had a lot of applications of origami in systems and technology. For instance, the pseudo bellows theorem, which states that a polyhedron cannot increase its volume while having rigid faces. But this can also be cheated by allotting for using a more stretchy material or introducing slits. Elastic origami, which is where simulating and designing origami whose form is governed by the equilibrium of forces from the elastic bending of each panel. Overall, this shows the different applications of origami in science and vice versa. Lastly, here are some more references for further investigation. Thank you.